So in the first video, we built this phase locked loop circuit in Gen tilde, which allows us to synchronize an output phasor to an input phasor gradually over time through this control loop that we implemented. And for this second part, I thought we could build something a little bit more complex based on this first implementation. And the idea I had was basically based on this idea of spontaneous synchronization that you may have seen, where you have multiple metronomes that stand on a shared platform, and since through this platform they all influence each other, you basically get this spontaneous behavior where they start to synchronize with each other after some time, which is a fun thing to watch. And I was thinking if we can use this PLL loop to achieve something very similar to this in Max. So what we can do here is that we copy this phasor and now we want basically multiple instantiations of this phase locked loop, but we want the same input phasor to be the master clock for all of them. And using the MC or multi-channel feature in Max, we can duplicate this phasor a number of times. So with the number of channels, we can set how many phasors we want. Let's say that we want to do 8 phasors. And now with the MC scope, we can see these 8 channels, which now will be exactly in phase because we have just duplicated this first phasor 8 times. But then we can copy this Gen PLL implementation and just prepend MC here. Then we will have 8 of these phase lock loops in one object. And now one thing that we can try is to change a little bit the behavior here of this MC PLL, because one thing we might want to do is to set the frequency independently to the 8 PLLs here. So we can change the behavior so that frequency instead is a signal inlet number 3 instead of a parameter. And then we need a third inlet here. So we still have our phasor input, we have our lock input, and we have a frequency input. We can copy this lock input signal from here, and then we can make an MC signal with 8 channels, and we can send this a message like 0.5 to set the frequency. So now if we do an MC signal number box, we can see that our 8 frequency channels here are 0.5. So let's put this as an input to the frequency of the PLL. Then let's add again a MC scope, and we can change the range to 0 to 1. Now we can try sending different frequencies to the different PLL oscillators. And one way to do this is to send a spread inclusive, which will spread these signals, including the edge values, between 0.4 and 0.6. So now the frequencies are a little bit different for all PLLs, and you can see that they start desynchronizing. And now if we go back to frequency 0.5, they have exactly the same frequency, but you see that they have gone out of phase with each other. And the cool thing is then that if we lock here, we see that they all converge again to synchronize with this master phaser. One other small thing we might want to add is a possibility to randomize the phase. And then we can add yet another variable called randomize. As inlet number 4. And then we say here if randomize we will set the phase to a random value which we can sample from noise, and noise gives values between -1 and 1, and we want values between 0 and 1, so we scale it. And now if we send an impulse, so this button and the click object gives us a pulse like this every time we click, and we send this into the fourth inlet, which is the randomize inlet, and then we will randomize all the phase, all the individual phases of these PLLs. So we have lock and we have randomize. Like this. And now we may want to visualize this in a more informative way than this MC scope. So we can, for example, use this 8 phasors to drive cosine oscillators. And let's say that we unpack these 8 cosines. So if we look at this first output, we have a cosine synchronized with the first phasor. And then we can take a snapshot every 10 milliseconds. We can scale this from -1 to 1 to 0 to 127. And then we can make a small slider to visualize the state of this phasor. We may want to change to just an indicator. And now let's duplicate this 8 times. And we connect the different phasor outputs to their respective visualization. And now we can randomize them, and then we can have them interlock again over time. And here we still have our parameter A, which controls how fast we're locking. So if we decrease this a little bit, we randomize again, and then we see a gradual lock-in that is a little bit slower. We can go maybe faster. That's very almost instantaneous. Then maybe 0.1 should be fairly slow. Now you see it takes quite a lot of time before they start to converge. So additionally, we could try to do some sonification of this. And here I'm thinking that we want some kind of click that happens when these metronomes or visuals are at their extreme points. And we can do this by subdividing all the phasors here by 2. So every time the PLL phasor goes from 0 to 1, the output here goes from 0 to 1 2 times. And then we can add the what object, which will give in output a click or an impulse every time this phasor here wraps around. So if we visualize this here, we see some clicks, and if we randomize the phase, we see the clicks start to spread out in time. So now we can do a MC mix down to 2. So we go from our 8 channels down to 2 channels for stereo. And then we can unpack these 2 channels. Make a live.gain, reduce the volume a bit, and then our output. And now we hear a small audio click every time one of these phasors are at their extreme value. And when we lock them into each other, we will get this spontaneous synchronization behavior gradually over time. So that's it for this second part, and thanks for watching.